I'm Anil Kumar, and here is solution of question number 16, page 129, Nelson. An elevator is designed to start from a resting position without jerk. It can do this if the acceleration function is continuous. Show that the acceleration is continuous at t equals to 0 for the following position function. S of t equals to 0 for t less than 0 and is t cube over t square plus 1 when t is greater than or equal to 0. So what we need to do here is we need to find what velocity and acceleration are. Velocity is first derivative and acceleration is second derivative of displacement, right? So let's begin by finding, we know less than 0 it is 0, right? So when it is greater than 0, let's use the function s of t equals to t cube divided by t square plus 1, right? So we are working on t greater than or equal to 0. Velocity is first derivative, so we say v of t is equals to s dash t, and we'll apply the quotient rule. So the denominator here is t square plus 1 whole square. Derivative of 3 is 3t square for t cube times t square plus 1 minus t cube times derivative of this function, which is 2t, right? So you can simplify this. So let's open the bracket. We have 3t to the power of 4 plus 3t square minus 2t to the power of 4 divided by t square plus 1 whole square, right? So 3t square minus 2t to the power of 4, is t to the power of 4. So we could write this as equal to t to the power of 4 plus 3t square divided by t square plus 1 whole square. So that is the velocity function, right? You really need acceleration to show that the acceleration is continuous, right? So let's find acceleration now. So acceleration is derivative of velocity, right? So derivative of this function will be, the denominator here is t square plus 1. Actually, okay, that's fine. Let's continue. So I thought we could simplify that a bit, but we can't. So we have t square plus 1 whole square becomes to the power of 4. It's already 2 here. Derivative of the numerator is 4t cube. Let me push this a bit if that is a problem. And plus 2 times 3 is 6t times the denominator, which is t square plus 1 whole square minus t to the power of 4 minus 3t square times derivative of this function, right? So 2 times t square plus 1 times 2t, right? So don't forget that part, times 2t. That could be an error sometimes, and maybe that is the reason why you need me to solve this for you, okay? So now let's expand the numerator and try to find the answer. Now t square plus 1 is common. So before expanding, you should always look for things which are common. They will help you, right? So we have t square plus 1 as common factor, and within brackets we are left with 4t cube plus 6t. Actually, we could have taken 2t also common here, right? So I'll take it next time. Plus 6t times t square plus 1 minus, so we took t square plus 2, we have 4t times t to the power of 4 minus 3t square, right? So that is the numerator part, divided by t square plus 1 to the power of 4, right? So let's go one more step. So what we thought was that we'll take 4t also common. We cannot take 4t, but we can take 2t anyway. And nothing else is common. So we'll just expand, don't worry. So 2 square plus 1, and we'll take 2t common, so 2t. We are taking 2t from here, right? So we are left with, if I take 2t from here common, I am left with 2t cube plus 3 times t square plus 1 minus, I've taken 2t, so I've left with 2 times t to the power of 4 minus 3t square, right? Well, this is not necessary, but it helps. T square plus 1 to the power of 4. Let's expand. So we have 2t times, we can cancel t square plus 1 here, and we'll get cube in this bracket, right? So we get 2t, and within brackets, now I'll expand this. So we have 2 times t to the power of 5 plus 3 times t square plus 2t cube plus 3 minus 2t to the power of 4 minus becomes plus 6t square divided by t square plus 1 to the power of 4, right? Now, well, this is the kind of equation you have. So I'm leaving this space to answer the question. You can further go ahead with this and solve. Anyway, let's look into the solution part, which says show that the acceleration is continuous at t equals to 0. Now, this function, denominator is always positive and there are no restrictions on the denominator, right? That is the first part. Second part is, if I substitute t equals to 0 for acceleration, what do I get? So I get a0 as equals to 2 times 0 over 1, right? So we get 0. So at starting, the acceleration is 0, right? So it is continuous. So when it is approaching from either side of 0, right, less than 0 also it is 0, and afterwards also it is 0. Therefore, acceleration is continuous. So that is how you can answer this particular question, right? Now, another part of this question which I have not written here was, what happens when t approaches large value, when t approaches infinitely large value? So that was the other part. You will notice in this particular case that the degree of numerator is higher than the degree of denominator, right? So for acceleration we're talking. So the acceleration will approach 0, right? Since the degree of numerator is higher than the degree of denominator, it approaches, since the degree of denominator is 4 times 2, 8, right? 4 times 2, 8. Degree of numerator will be t times t to the power of 5, 6. So it approaches approximately t to the power of 6 over t to the power of 8. Do you see that? So since this is higher, it works like 1 over t squared. So as t approaches infinity, acceleration approaches 0. Now, as far as velocity is concerned, velocity degree of numerator is 4 and denominator also is 4, right? So since the degrees are same, so the velocity approaches the value 1 and the coefficients are 1, right? So their coefficients are 1, so the velocity approaches 1. So that is the part B of this question, right? We'll take up in another video also, but that is how you can complete the solution of this particular question. I hope that helps. Thank you and all the best.